So, the term, the IoT, really came from Kevin Ashton talking about empowering computers with their own means of gathering information so they can see, hear, and smell the world for themselves in all its random glory. That's quite poetic. But really the machines are happier if they're sensing. So the Internet of Things is very small. You have small microprocessors, small sensors, small amounts of memory, small messages, small antennas, and small wireless transactions. By small, I mean it's okay for an Internet of Things device to send 1 byte of information, 8 bits. This can cause problems when you're dealing with protocols that have maybe 128-bit long addresses. This can make it difficult for protocols like 3G, where to send 1 byte of information, you need about 10 transactions back and forth. So the Internet of Things is small. That's the biggest difference here. Of course, this is a lot of different chips on one little wafer. The Internet of Things is big, though, because today, your microwave, your washer and dryer, your dishwasher, coffee maker, refrigerator, all of these household appliances are starting to become connected to the Internet. There's a very disgusting and popular photo going around now about how someone put an inappropriate web page on a refrigerator at a store, because yes, refrigerators are now connected to the Internet. So this is the biggest cliche in the Internet of Things, the connected refrigerator. The connected refrigerator knows what you put in. It knows what you take out. It will tell you when you're running low on, this is Sri Lanka, so we're going to say anchor milk or anchor butter. And of course, it's from New Zealand. I love that. Your smart refrigerator could order more food for you, and it may know how healthy you are. But that is honestly just the cliche, because when we get into the Internet of Things, the first and most important things are going to be industrial things. Refrigerators like those that you see in grocery stores, in the supply chain for food, so the suppliers, in the producers of food. The reality of it is that in New Zealand, we now have government regulations to track the temperatures of all refrigerators that are involved in the food production chain. And the way people are tracking those temperatures now is by looking at a manual thermometer and writing the temperature down in a paper logbook. And if you have a lot of refrigerators, that can be a very time-consuming task. Today, we have temperature and humidity sensors that can be purchased for $100 that have 10-year batteries in them that you can stick in a refrigerator. You don't have to run a local area network. You can attach to a wide area network that may be 1, 2, 10, 20 kilometers away. Put the $100 device in your refrigerator and forget about it for 10 years. That's the reality of the Internet of Things now. Heating and cooling. Heating houses and buildings is a major use of electricity and gas, and right now it's very uneconomic and unscientific. In this building, for example, the temperature is all over the place. We had a problem a few days ago where some of the rooms were maybe 20 degrees and some of the rooms were maybe 12 degrees, and people not used to the cold were freezing. Can we do better with IoT? Absolutely. Because now the thermostat for a room like this may be one little box on the wall, and that is the one data point that the system gets for supplying air to this room. They think, okay, if that one spot is correct, then that's what we're going to do. Maybe the sun is shining on that one spot. Maybe somebody's set a pitcher of ice water next to it. The Internet of Things means that we could have 100 temperature sensors in this room without spending a lot of money, without going through expensive retrofits of the room. And with that small amount of technology, we could start saving on electricity and gas. So the Common Thermostat, this is a common thermostat that you'd see on the wall in a house with a heat pump. It requires daily human intervention. It relies on very limited amounts of data. It sometimes works. A company called Nest built a better thermometer connected to internet via the Wi-Fi, learning the habits of when you're turning it up, when you're turning it down, when you're in the house, when you're not in the house. And Nest became the first successfully sold Internet of Things company. Google bought them for $1 billion 3 years ago. because it was such a great idea. Meters, gas meters. Now, someone comes around and reads these meters with their eyeballs every month or every 2 months so that they can send an invoice. And it's kind of different with electricity meters, because electricity meters, it's easy to put an electronic device with power on it because there's power there. It's an electricity meter. Gas meter, there's no power there. Water meter, there's no power there. So you need a small battery-powered device that will last a long time, because you don't want to be going around and changing the battery every year. That's almost as bad as going around and reading it every 6 months. So these meters frequently have no sunlight. For water meters in Australia, in many cases, they're located under ground level. They'll be in a small pit about this low with a plastic cover on top. These meters are hard for humans to read, hard for them to maintain, and new technologies, new batteries, and new wireless protocols in the Internet of Things solve this problem already. In Australia, there are hundreds of thousands of water meters located below ground level that are using IoT technologies on batteries that will last for 10 years. Problem solved. Power meters. Well, this isn't just a power meter, this is a substation. This is a transformer from high voltage down to household voltage. IoT is not just for metering. Those transformers back there, they're filled with oil. They last around 20 years, and they cost a lot of money. But nobody knows exactly how long they're going to last. They may last 20 years and 1 day. They may last 19 years and 6 months. The thing is, if you take it out too early before its life is over, then you lose money. But if you leave it in too long, it goes bang. It actually blows up or stops working. What can you do to fix this problem? You can put temperature monitors inside and on the side of the transformers, and you can graph that, and you know that things inside the transformer are starting to break down when the temperature rises too high. You can monitor voltages. You can see when there are starting to be voltage instabilities coming out of that transformer, that perhaps it's time to replace it. So you can extend the life of existing infrastructure using IoT technology. Yes, this is a mouse, and there is the old saying, build a better mousetrap and the world will beat a path to your door. So there's a regulation in the UK that mousetraps be cleared within 24 hours of having been used. So in the UK, in a supermarket, they go around the supermarket every single day with a stick and a mirror on it. And they look behind the shelves, under the refrigerators, all over the store at every single mousetrap that they have installed to see whether or not it's gone bang and said goodbye to the poor mouse. This process has already been automated with IoT. 3 years ago, a company called Newell, who was 2 years ago acquired by Huawei, built a mousetrap that sends a signal when it's been tripped. So now they save the labor that was nearly an hour a day for some employee looking at the mousetraps for a very, very small amount of money. So, okay, trash can in a city. This is a municipal application. In Milton Keynes in the UK, there are smart trash cans. It used to be that city employees would run around looking in the trash cans to see if they were full. And now at the bottom of the trash can, there's a load sensor. And you don't see this. You don't see any sensors. You don't see any antennas. You don't see any cables, nothing, because it is an IoT device with battery power, a tiny embedded antenna, and it will signal the load on the trash can so that the city knows when to send the truck around and pick it up. Diesel fuel is an amazing expense for cities who send trucks around to pick up garbage. So they save time, they save diesel fuel, they save people hours, and they keep their city clean. Lights, okay. Street lights are not on during the day. They're only on at night. So in order to know if your street lights are working, you've got to send somebody around once a week to look at all of the lights at night and see if they're functioning. Or you could wait for a report from the public, like if you're my city council, a street light will go out and they'll wait until 10 people call to fix it. Inexpensive IoT sensors solve this problem. What do? They monitor the current being used. If a light stops using current, then they know it's not shining anymore. So they send somebody around to fix it. In large cities on highways where streetlights are public safety, cities really do send somebody around in a car every week or every month to check all of their streetlights, and it is an incredible expense. So now, when they replace their streetlights, they're putting these sensors in, and sometimes proactively they're replacing their streetlights, putting the sensors in to take that piece of maintenance out of the running of their city. Car parks, okay? You may think finding a car park is trivial, but really, having free car parks is the most important thing for a city to reduce its traffic load. Most traffic in a city is actually traffic that's looking for a car park. This has been proven, and there's lovely optimization studies and so on. So better parking information means less driving around, less traffic. Garages with IoT sensors in them, and we have them in production in New Zealand now, can tell you the number of free car parks. You see this in Singapore too. You're driving by the building and there's a big electric sign that says there are 350 car parks in this facility, free. There are 10 car parks in this facility, free. Come on in, park your car. These sensors happen several ways. Sometimes they happen by light. You put a light detecting resistor in the middle of the car park, and if a car is parked over top, the light goes out. Other ways, they put reed switches so that if there's metal near, the switch will close and they send a message, metal being the engine block. So, supply chain, containers. What is in that container? If that container is coming from New Zealand to Sri Lanka, it could be full of cheese or butter or milk. It could be full of electronics or coffee. If it's full of butter, can it get hot? How hot can it get? If it's full of electronics, can it be shaken? What happens if it's dropped? Can it get damp? IoT sensors can record the conditions of these containers, and they may record these conditions the entire route from the factory where the container is packed all the way to the recipient warehouse where it's unpacked, and the owner of those goods can then get that data and know if the goods that they've delivered are actually going to be good. This is amazing. The container port here is just right across the street, and it's gigantic. I can't believe how many ships are in there loading and unloading containers right now. So where is your container? Tracking containers used to be a problem that cost thousands of dollars because modems require quite a lot of electricity to run, GPS receivers, a lot of electricity to run. The electronics and housing was all quite big and quite expensive. You can now do GSM-based tracking with IoT technologies and batteries for less than $100 anywhere in the world that has GSM, or you can do satellite tracking anywhere in the world even without GSM networks for less than $500. And if you do it for tracking, you can use that same system for the telemetry, like the temperature and the humidity and whether it's been broken or crashed. This is a light. This is just a generic lighthouse, but in fact, another of my customers in New Zealand is a harbor authority, and we have instrumentation on their lighthouses. Maritime lights are like street lights, except they're much harder to check. It costs the harbor master in New Zealand tens of thousands of dollars a year in fuel to send a boat around at night to check the safety lights. Now, in the large shipping lanes, the ferries who run the route every day will call in and report that a light is out as soon as it happens. But in the smaller bays, people don't go there every day. And yet, if a light goes out, some guest sailor, because it's a beautiful place and people come from all over the world to sail there, some guest sailor may miss the light and may ground their boat. They may cause harm to the environment because it's a very sensitive environment. So knowing if the lights are working, incredibly useful. But also the harbor authority can use these lights because they're fixed places with a little bit of power to get weather data or tide height. They can use them for tsunami warnings. There's a whole range of applications IoT is suited for harbor operations. And the technology is actually an order of magnitude or 2 orders of magnitude cheaper than it was just 5 years ago. Irrigation. The pivot irrigator it's the only reason that you get milk and butter here from New Zealand. About 1 million hectares of land in a place called Canterbury, New Zealand is irrigated with pivot irrigators. Right now, the irrigators, for the most part, just water and water and water. Even if the ground is already wet, they don't know. Modern pivot irrigators have sensors in them to know how much water to put down. They can vary the size of the nozzle in real time so that less water is delivered to places that are more wet. Saving water, saving the aquifers, making sure that we'll be able to continue supplying milk to the world in 10 or 20 years. This drip irrigation technology was actually pioneered in Israel, where they now grow enough fruit and vegetables in a desert to export to many countries around them. I think Egypt is a major consumer of produce that's actually grown in the desert in Israel with drip irrigation technology like this. Soil types and drainage varies greatly across farm fields. Having moisture sensors in the soil can enable a very high level of detail so that you know how much water you should be dripping out of each one of these little holes. Now, this is a much harder problem than a pivot irrigator, but there are ways of controlling it. So water savings can come at the drip level, and I have at home in my house in New Zealand implemented a drip irrigation system with 50 plants. So I have 50 little tiny sprinklers, and I haven't put soil moisture sensors in yet, but I really intend to. Greenhouses use a lot of natural gas, LNG, CNG, to keep them warm at night, but they really don't know how much they need to use. They just turn the heat up when it gets too cold. Having lots of temperature sensors, again, just like in this room, having lots of temperature sensors can lead to less use of gas. Also with water delivery, it really drops the cost of industrial systems and opens fine control of machines for all markets. Right, water tanks. This is a water tank. There are, how many? 4 million households in Australia that have water tanks, mostly for taking the water off of their roof and keeping it as a standby supply, either to flush their toilets and water their garden, or also to drink, because they don't have a suitable city water supply. Checking the tanks to see how much water in it is a manual process. People will go in situations like this, tap on the side of the tank, see if it's full, or they'll climb to the top, they'll lift the lid on, they'll look inside. You can now build a tank monitor sensor, uses ultrasonic, permanently attached to the tank. You can build one for less than $100 that uses 3G. And I wrote this slide deck 18 months ago. Since then, we're now down around the $50 mark using technologies like LoRa or SigFox to take a reading from an ultrasonic sensor and send it back to the cloud. There's a water tank on top of almost every house in this building because the water supplies are intermittent. So throughout South Asia, there are neighborhoods, I remember in Nepal, there are neighborhoods where the water isn't on all the time. When the water is on, people have to go and turn their electric pumps on, so they pump the water from the street level up into the tanks on their roof. If you have water in a tank on your roof, you have no idea when it's going to run out. You don't know if you should be washing the dishes or doing the laundry or taking a shower or not. IoT meters can tell you when you're going to run out. Connected meters, as in if a city has that data, can know how is the city doing in terms of water? Is the city about to have a crisis, or is everybody's tank full? Right now they don't know. They just turn the water on and they give as much as they think people need, and then it's done. Right. Water delivery. Yes, water runs out, trucks deliver more. Where should the trucks go? When should they go? Using connected meters can help the delivery firms know where they need to drive, what route needs to be optimized to use the least amount of fuel, the least amount of time to deliver the most amount of water. And yes, sometimes there are times when there's too much water. This is Bangkok, I want to say 2011. Up at AIT, it was flooded quite a bit. Flooding is a difficult thing to track before the days of the IoT, but Project NOAA in the Philippines has deployed 1,000+ IoT stations using small microprocessors and things like 802.15 to mesh the wireless back and forth so that they know when the floods are going to come before they happen. They know when the mudslides are going to happen. They have sensors in the soil on the sides of the hills that sense for shakes. They have water level sensors in all of the streams. They have rain gauges on all of the hills. So they know to alert people before a mudslide happens, before flooding in a city center happens. And this is something that could not have happened before the IoT technologies that we're going to talk about. So, can I have the next slide deck, please? Next slide deck, we're actually going to talk about some of the technologies. Yeah, okay. Okay, I'll breeze through this one too. No, can I have the other next one, please? There we go, the radio frequency protocols of the Internet of Things. Yes, the big devices use Wi-Fi, but Wi-Fi is not necessarily an IoT protocol. What's an IoT protocol? One that is optimized for low power, low CPU, low size, optimized for the constraints of radio networks used in difficult situations, propagation issues where you may have to get a signal from under a trash can, from under the ground on a water meter. From situations where your radio power utilization is the #1 contributor to how long your battery is going to last. If you have a inefficient radio protocol, your 10-year battery may last 1 year. Dealing with interference from yourself or other devices. The density of devices in IoT is going to be orders of magnitude greater than any other wireless network we've ever imagined. I know Wi-Fi is dense now, and for each of you, we probably have 2 or 3 Wi-Fi devices. IoT may exceed that. So 802.11bgn, it is pervasive, it's everywhere, it's low cost. There are more than 1 billion 802.11 chipsets made every year. The last time I looked at the numbers 2 years ago, there were more than 7 billion active Wi-Fi devices. You can now get a microprocessor with a Wi-Fi module on board the size of your finger for $7. That's a whole computer with digital inputs and outputs and a Wi-Fi chipset and some memory and so on for $7. So this is the default protocol for connected devices like your refrigerator, like your thermostat. It works where there's power, it works where there's Wi-Fi, but Wi-Fi doesn't solve many of the IoT problems. So the first IoT protocols came out, I want to say, even 10 years ago. 802.15, several variants of 802.15, including, so 802.15.4 would be like Zigbee and Bluetooth Low Energy. These operate at range of frequencies. I've left out China in the 760 range. There's a 433 range, but Zigbee, Bluetooth, and BLE almost exclusively operate at 868, 915, and 2.4 gigahertz. They can run at anywhere from 20 kilobits per second to 1 megabit per second. So this isn't broadband, this isn't Wi-Fi. Wi-Fi is gigabit these days. Wi-Fi is hundreds and hundreds of megabits. So this is orders of magnitude less. 20 kilobits to 1 megabit, depending upon how much spectrum is available. You can put them in a star topology, in a tree topology, in mesh topologies. They are low power consumption, and they are very low cost in the 2.4 gig band. In fact, I have my bag here, so I'll just take one out. Oh my gosh. I have little Bluetooth low energy things just everywhere. Here's one. This is a Bluetooth low energy tag that I keep in my wallet. And anyone who's using the app Tile is actually receiving a signal on this and sending the location data of this device to the cloud so that when I lose my wallet, I'll be able to find it. That's a big version of a tile. I've got another version right here. This is on my key ring here. What happens when I lose my keys in the house? I click a button on the app, and this thing sings to me. It actually has a speaker built in, and it plays a little song loud enough that I can hear it. And these batteries are good for a year or more. See how thin that is? It's a computer with a chipset and a battery that lasts a year in that little tiny wafer. That's using Bluetooth Low Energy, so one of these 802.15.4 protocols. So we started, I'd say, 6 or 7 years ago, having IoT wireless protocols based on very inexpensive chipsets, serial, just basically wireless serial, 433, 868, 915. There is a chipset called the RMF69. There are open source libraries for it. You're talking 1.2 kilobits to 300 kilobits, so whereas 802.15 was like 20 kilobits to a megabit, this doesn't get more than 300 kilobits per second. You're down at the point where you can probably start using a snare drum to beat out the pulses on this. It's really, really low speed. On the other hand, the receive sensitivity can be fantastic. Now in this decibel meter, each 10 dB, it's a logarithmic scale, so each 10 dB is an order of magnitude. Wi-Fi chipsets receive down to around -90. So these technologies are 3 orders of magnitude better in terms of coverage, in terms of hearing faint signals than Wi-Fi. And that is really, really significant. It means that I could leave my wallet with one of these devices in it. I could leave it at the bottom of a building and still find it from the top of the building, through all the floors, because the radio will just propagate through. These particular protocols are star topologies. They're very, very inexpensive. When I say $3.50 per module, this means you've got a microprocessor and digital inputs and digital outputs and a radio transceiver for $3.50 US per item. And that's for like buying 10. You want to buy 10,000? Probably $2. Who knows? Very, very, very cheap. Dash 7 was something that the US military put a lot of effort and money into. When I first researched Dash 7, I thought, this is fantastic, this is really great. And there have been no civilian applications, and you just can't buy the technology, so I should pretty much ignore it. But it builds on these wireless serial protocols by adding AES encryption. 1 to 10 kilometers, encrypted data, very low bit rate, fantastic. Z-Wave, I know somebody around here was talking to me about using Z-Wave in their house to do smart home things. 32-bit address on these Z-Wave devices means that the use is limited to homes and businesses. It's not a wide area device. And they are mesh-powered repeaters. In a mesh topology, devices need to stay on all the time listening for messages from other devices so that they can relay the traffic on. Or they have to all as a mesh agree to shut down and save battery and wake up at a particular time and exchange their messages. Mesh topologies are very inefficient for battery use, which is why none of the new modern IoT protocols that have come out in the last 3 years are mesh topology. They're all star topology. SigFox is very, very interesting. It's also very proprietary. It's a French company that has come out with a protocol at 868 and 915 megahertz. They started as a transmit-only protocol, as in the devices would only send 12-byte messages, maximum of 140 12-byte messages per device per day. So this is not for getting temperature readings every 5 minutes. Not at all. This is for reading a meter or reading something that doesn't change frequently. It can go as slow as 10 bits per second. There is some encryption, I don't understand it, but the strange and interesting thing about SigFox is they are the only network operators in the entire world. This one company, SigFox, gets into agreements with carriers, with cell companies around the world, but SigFox still owns the network. Anybody can buy a device and get on the SigFox network for soon $1 a year per device. But SigFox gets all the money. They're the network operators, so it's not exactly an open system or open protocol. Now, LoRa, on the other hand, is the network that I'm operating in New Zealand and Rarotonga. It is open in that all of the software protocols are published. It is open in that anyone can buy a LoRa gateway and run their own LoRa network, unlike SigFox. It's closed in that only one manufacturer is making the chips right now. They will license the chip design to other parties, but it is very much like 3G, 4G, where companies like Qualcomm control the core intellectual property that's used inside the chip. So it's not 100% open source. I find it to be a great solution for a number of IoT problems, less than a kilobit to up to 50 kilobits per second of data. How fast you transmit depends upon how fast the base station tells you to transmit. And that depends on how much signal the base station is getting from you. So if the base station says, hey, I can hear you loud and clear, I've got a great signal from you, the base station is going to say, right, you talk at a very high modulation. You talk very quickly. If the base station says, hey, you're coming in really faint, the base station will tell the device, hey device, why don't you talk very, very slowly so I have a lot of time to think about what you're saying to me. So in our network, we're seeing 8 different levels of modulation of data coming from devices out in the field. LoRa protocol has multiple levels of encryption. The application owner, as in if you're the owner of this facility and you have a bunch of temperature sensors, the application owner gets to encrypt the data from their application, so the network operator never gets to see that. The network operator gets to see the metadata. They only get to see some data came from a device at this time, and that's it. On the outside of that, the data packets themselves are encrypted so that a casual observer or a hacker can only see that some packet of information went. They don't know that it's a LoRaWAN packet. They don't know what's in it. They don't know who the end user is, and they don't know who the network operator is. They just know there's an encrypted packet coming through the air. Weightless and now nb-IoT. Weightless started and still is a completely open standard. The Weightless Consortium started out writing an IoT protocol for TV whitespace. They said, right, we've got all of these unused TV channels, let's run the Internet of Things in them. The one company that was making a production chipset for Weightless was purchased by Huawei 2 years ago, and the technology is now being integrated into a protocol called nb-IoT, or Narrowband IoT. Narrowband IoT is much like LoRaWAN, except it's going to be run in the radio carriers that are on each side of a 3G or 4G cellular carrier. So one cellular base station is just going to add a bit of software to add the nb-IoT signals to the sidebands of the 3G, 4G carrier. Yeah, it's really cool. It has public key encryption. It supports itinerant nodes, as in nodes that are moving. It's not a true mobility solution, but it's okay to take a device from one base station to another base station. It supports really intelligent scheduling, so the tower and the device can negotiate for the device to go to sleep for, say, 13 days. And the tower will know that the device is going to wake up in 13 days, and the tower will have a time slot ready for the device to wake up, send its data, and go straight back to sleep, thus saving its battery. Again, 10-year lifespan is the goal there. Last one, LTE-m, is 3GPP, before Huawei introduced nb-IoT, decided that LTE needed to be extended to support machine-to-machine communications. This is a replacement really for all of the GPRS Coke machines and GPRS telemetry out there in the world. They call it Cat M1. It's going to be included in the next release of 3GPP. You're going to, as a cellular operator, be able to run this alongside of your LTE with the same base station. It takes a very small 1.4 megahertz carrier, divides it up into 6 230 kilohertz carriers, and has some of the same features of these other modern IoT protocols. But it is something that is going to be run only by cellular operators and only in licensed cellular spectrum, whereas SigFox and LoRaWAN are in unlicensed ISM spectrum. So I think that's about it. The rest of this is a bunch of exercises. Can you put Kaysen's slides up now? Fantastic. I'm going to turn over to Kaysen, who's going to talk about the layers 3 through 7 of IoT. Up to you.
Good morning, everybody. My name is Kalsun Dizoisa. I am a senior lecturer for University of Colombo School of Computing, Sri Lanka, as you may see. First of all, I would like to thank you, APNIC and Jonathan, to invite me to share this tutorial. In my tutorial, mainly I will discuss a few interesting IoT applications. We do it here in Sri Lanka, as well as the challenges we have to face if you have real-life IoT applications. So in the technical point of view, there are several components if you want to build your own IoT application. The first thing is basically we need to identify them to find it out, the unique ID kind of. And then we need to have communication interface. Jonathan explains basically these protocols we use, like Zigbee, Bluetooth Low Energy, and LoRa, the newest things like that. And on top of those, we need to have kind of protocols which communicates them and interact with them. Of course, finally, if you want to have real-life IoT applications, we need to think about security point of view. So how do you secure them? So I'll discuss in my presentation those things. Identification point of view, how can you identify them? Maybe we can use, someone can propose perhaps IPv6 address. Someone can propose maybe the DNS, we can have kind of a DNS address. And maybe some object identification system. Somehow there are no unique method right now. Different vendors, different protocols use different technologies for that, or different types of methods for the identification. Then the second problem, as I said, the communication. How do you do the communication, scalable communication? So whether it be UDP or whether it is TCP or something else, or how do you handle it in the host-to-host or like kind of object-to-object, device-to-device, and so on. So we need to think about kind of communication we need to use. And as Sean also mentioned, there are kind of common communication protocols nowadays used by those IoT devices. Few of the popular protocols I have a list down here. So for example, one of the popular protocol X6 low PAN. So that is low power IPv6, IPv6 low energy, for low energy protocol for personal area networks, 6 low PAN. And the other one is CoWIP. And then there are a few other protocols I'll just highlight before I move on to the other interesting part of securities, like MQTT, REST, HTTP, and of course WebSockets. So they are the kind of communication protocols we can use in our IoT application. IPv6 over low power wireless area networks are basically kind of used by most of the devices, some practical IoT applications. So they can establish IPv6 channels and they promise kind of end-to-end encryption between that, but unfortunately, even though they say so, we have to break that encryption at the middle because there are kind of conversion, they are IPv6 stack kind of a low match to the low energy, but if you want to talk with the real device, perhaps they need to break their encryption at the middle. And also they have like, since they are IPv6 and the IP-enabled devices, of course, we could use that. So the question researchers asking is whether IP is the best way to identify these devices. If so, of course, IPv6, this protocol may work. If you have different identification system for those devices, maybe we cannot use this. And then other protocols we use by those devices are CoAP, It's called Constrained Application Protocol, especially to develop to a kind of object interaction between. So that's mainly developed for machine-to-machine interaction. So that's quite popular, and most of the IoT platforms out there use co-op messages in between to communicate. And UPnP is kind of another practical protocols we use day-to-day IoT applications, like especially in the Wi-Fi. So in order to identify the Wi-Fi devices which connect to the access points, we use this. And then they can automatically connect it to our access points and connect to internet and communicate. So practically we use this protocol. And then lightweight machine-to-machine interaction protocol is kind of other protocol which we can use to kind of machine-to-machine interaction. So it's another protocol we could consider. MQTT is one of the other popular protocols which do machine-to-machine interaction. As I mentioned, there are several IoT platforms out there which you can directly use. Some of them are open source, some of them are commercial. They use MQTT messages and they support it. And also hardware devices, there are MQTT supported hardware devices there which use this protocol to communicate.
I'll just add that MQTT is a very popular protocol for LoRaWAN, and many LoRaWAN base stations include MQTT software in their stacks.
Yes, thanks, John. So that's kind of a very popular one which communicate used by the devices out there in the industry. And if you want to have kind of web interactions with these IoT, REST is some protocol which you can consider, especially on the HTTP, because you know some firewalls they drop the UDP traffic in cases. So there we have to use TCP and HTTP. So if you use HTTP only kind of interaction, REST is a protocol where we can think about for this interaction. And then for the browser, like in the other protocol which we could use to IoT communication is WebSockets. Perhaps you heard about it. This is a kind of a protocol where using web browser can communicate each other, like using your socket-like interface. It's a socket stream connection over the HTTP. Even though we say so, it's initiation or the negotiation of the things goes on the web. So especially we use that to kind of fool the firewalls. Like, so if firewalls only allow web traffic, we can use web sockets. So then firewall think is a web, but we can communicate whatever the data in between those devices using web sockets. So mainly by looking at these protocols and develop our IoT application, we have two kind of architectures, two main architectures where we can use. One of the architecture, of course, everybody knows client-server architecture. So client requests something, server process and provide it. So most of the protocols like WebSockets and REST use that architecture, you guess so. So the clients request the data and the server provide it. So in the web, if you use web, of course, you know, we have to keep that connection alive, like we use kind of technologies, what we call push notifications and so on, or else we have to use WebSockets. And there the devices can communicate each other. But for the IoT, most of the IoT application not based on client-server architecture, based on the architecture what we call publish-subscribe architecture. There are all the IoT devices, they publish their information to a kind of cloud servers, and interesting parties can subscribe to those channels. So then cloud creates kind of control some servers. So any devices, they regularly pump the data, maybe temperature or whatever the data to the cloud, and then server can allow other parties to subscribe those information, interesting information. So there are platforms which supports that operation. So then subscribers, using some events, subscribers get those data. So then they can work on it. So most kind of popular IoT application development architecture is this. Of course, if you use IoT application, we cannot forget about security and privacy. As Jonathan mentioned, he has a Bluetooth Low Energy wallet tag. So you should know, not only John, maybe if I can see where his wallet is if I have some apps. So that's kind of a question. So if I know his wallets, perhaps I can take it, right? Right? So similarly, if you have any kind of IoT applications, it's a question. Security is always a question. So there are quite interesting applications out there, which location tracking application, you can find your location of the friends and so on. So those applications upload your location regularly to the cloud servers and as a publisher of the information. So then as a subscriber, your friends will subscribe to it. So of course your friends can see it, maybe this cloud provider can see it, maybe someone hack into that cloud provider can see where you are, what you did, and where was your locations and so on. So privacy and the security is kind of a question when you practically start using those applications. So how do you solve it? So it's not so easy to solve that because it's kind of a hard problem, complex protocols and millions of devices and different kind of interactions. So it's very hard to solve this security problem. So sometimes we cannot use a standard encryption or the standard cryptographic things we know, such as public key encryption or the symmetric key encryption. On that we need more than that. I'll discuss in a minute. So then there are two problems of security because the security is made hard. One is we have to think about the communication security, that between the communication between device. So it's just kind of client server, so that's communication like at the server. So then server, of course, see it. So the other problem is how do you store those information? If you store those information of the clouds, of course, they don't store the encrypted data. They store the plain data. So service providers plus the people who access to those authorized or unauthorized people may get those information. Right, so let's have a look first what kind of security protocols which used by these right now with this communication for IoT communication. So actually we use quite popular existing internet security protocols to protect the communication between those devices. So what you should understand, all of them are communication security protocols. So for example, TLS, so that is SSL in other words. So some of these IoT protocols, they use SSL or the TLS to have transport layer security. TLS means transport layer security. Or maybe if you use IP, low power IP, low energy IPv6, so we can use IPsec perhaps to encrypt this channel. And then maybe SSH or SSTP. Or if you use a UDP-based communication protocol like MQTT, so we cannot use TLS there. There we have to use DTLS. So it's kind of a variation of TLS protocols which can work on top of UDP. Since network guys, UDP is connectionless and the TCP is connection-oriented kind of protocols. So in the TCP communication, we can use TLS for the UDP messages. If in case of the IoT protocol which use UDP, we can use DTLS. So that's the standard communication protocol. That won't support the storage. How about the data? So for example, if you use the data, so there is a device which supports DTLS, maybe MQTT, we publish those information to the cloud. So this cloud storage. So whatever other parties may subscribe to it. Of course, from me to server is encrypted using DTLS, and the data will store in the plain text form on the servers, and then from the servers to your whatever the subscribers, it's encrypted, of course. But the data itself stored in there in the plain text form or the unencrypted form. Otherwise, this system may not work, because if it is not encrypted, how do you find it out? We have to send this data. How do you run kind of statistical queries on that, such as things may happen. So then what would be the solution for that? Some of you might know there is a new kind of encryption algorithms people are looking for to solve it. Let's call it as homomorphic encryption algorithms. Perhaps you heard about it. So I'm not going into mathematical detail of it. Basically, homomorphic encryption says we can store the encrypted information on the clouds and still process it. So whether it's possible. So that's quite interesting, because then we can use publish subscriber architecture without any worries. So we can use existing encryption protocols between the communication protocols between device to the server, and send the homomorphic encrypted data, and that encrypted data is stored on the servers, and then other parties can subscribe to that, and then they can decrypt and view it. But the server is then blind, because the server will have encrypted data. But basically, if you use the traditional encryption systems and install the encrypted data on the servers, the problem is servers cannot process it. So the idea is, so for example, I have an example here. So for example, there are two devices here called, maybe let's say some temperature or whatever device which measure some values. So when these values are 7, 10, and 7. So the homomorphic encryption says we encrypt those values based on the homomorphic encryption. Let's say encrypted ciphertext, encrypted data is X and Y. Instead of storing 10 and 7, we store X and Y on the server. So server cannot see that. So of course, if server cannot see that, if someone want to add them together or process it, server cannot process it. But if you encrypt it in the homomorphic way, we say server can still process it. So for example, if server wants to multiply it, they multiply encrypted values together. So that is X and Y. So the result in kind of encrypted format, and then that will go back to the other subscriber devices in the encrypted format. Device can decrypt it and still get the normal results. In other words, let's call it as we multiply the plain text, get the same results, but we multiply the ciphertext also, we can get the same results. So that's the idea. So there are several algorithms out there, people trying to do it. So some of these encryption algorithms we already have, such as RSA is partially homomorphic, but people are looking for fully homomorphic encryption. Partially homomorphic means for some operations like plus, multiplication, maybe they works homomorphic, but for others it may not. So if you can find some kind of homomorphic encryption algorithm which works in that way conceptually, then we have no problem. So we can perhaps store the encrypted data on the server, and we have quite good privacy. Right. If not, what can we do? So I'll discuss in a minute. So right now, there are several IoT-based platforms which use end-to-end encryption. Not end-to-end, it's actually device to the server kind of encryption and support us to build IoT application. One of such platform is PubNub. So they support MQTT and kind of other open IoT protocols, and they provide publish subscribe channels so people and interfaces people can easily build. So this kind of a commercial platform. And then we have Azure from IoT Hub from Microsoft, and they are also kind of a thing. Same kind of hub. So you can register your devices, and then it use again the same architecture. So their devices could use whatever their messaging formats, and then upload those to those servers, and then server will distribute to your interesting devices. They are not using homomorphic. Any of these existing platforms, they are not using any kind of encryption. So they support security. Security means the device to the server is used. They might use DTLS or TLS. So that's what they mean by the security. And also AWS, Amazon also have their own IoT hub. So they also support existing IoT messaging between the devices through their IoT hubs, and using the same publish subscriber kind of architecture. So they use communication security and not data storage. So all of these platforms, the common kind of things in all these platforms are, they support publish subscriber, and they provide the security between device to the platform, and then platform to the other device. And most of them are basically actually commercial platforms. You have to pay if they use them. So as a kind of researchers in the information security domain, we thought of having kind of open platform. We can have a little bit better than them. So by what we try to do it with that, basically having kind of end-to-end encryption using public key cryptography, messaging formats. We have developed kind of messaging formats which could support end-to-end encryption through a server. So there we could have end-to-end encrypted communication between two devices. So we call that platform as Sensi platform, or we short name, we call it an My Sensor, because our all kind of IoT devices, sensors, our sensors can connect to each other. So in the scalability wise, if you have millions of devices going through one switch, maybe not kind of scalable in this platform, there we thought of like having devices which personalized set of devices which belongs to me can talk to each other in kind of secure way without exposing the data to a middleman. So that's kind of idea we had. So other thing is we create a kind of interface which could use to interact with the device to device, that is machine to machine, and also to human to machine. So that still, if there are no interface device, if other end is a human can see what this device tells, can interpret. So for that, we develop some kind of language which humans can understand. So you know, everybody knows Twitter, and I think everybody uses Twitter. So we use kind of tweeting notations to describe this. So the machine can interpret, plus human can interpret. We get these messages. So for example, so let's say there is a device called D1 which belongs to me and want to share some information, temperature to me, for example. So there as a human, there is a device first called D1 need to tell he is going to share the temperature to the cousin. So then the router or the platforms knows it's going to share the data. And then, so after that, I could access the data. So there is a method called get. So then I say get the temperature from the device D1. And maybe I can add for some days or for maybe periods and so on. So then, of course, the device can interpret it and then give me back the temperature as I requested. So all the temperature is basically encrypted, not total message. Value is get encrypted, and whatever the data passes are digitally signed. So then no one can tap, but the confidential data, since they are encrypted, no one can see at the middle. So that's the idea. Similarly, I can provide more examples how we can use that. For example, let's say someone wants to access the switches, so which connected to the Raspberry Pi GPIO port. So then device should start and tell, so it's going to share GPIO port 1 to me, maybe cousin, and then I get that query, and then I can ask to control that device. Like say I can turn on the light connected to that or turn off the light connected to that by accessing it. So in this, basically the device voluntarily say, I want to share my whatever the sensors or the actuators to the person. So after that, this person can control it. And plus all the communication device can do encrypted way or kind of unencrypted way. So in that way, we can encrypt the sensitive data only and the key pressed. But all the messages are digitally signed. That means we provide the integrity plus authentication of the communication. No one can alter at the middle. So for example, it could use for even share the location between two devices. Maybe devices can maybe phones. So if two people wants to share the location of each other, maybe one can share its latitude and longitude to the other person, the mobile device, and then he could access the location of the person interested, and then that person can encrypt and pass that data to the interested party. So at the middle, cloud may not see it, or whatever the cloud IoT platform which provide this service even may not see the locations. So its devices directly access the data from the other devices. So the middle platform is basically supporting this communication. So using those platforms, there are quite interesting applications we are developing. Maybe if you interest them, you can interact me after the sessions. One of the kind of application we are developing is IoT application to solve the human-elephant conflicts. Actually, it's some kind of a problem here right now in Sri Lanka. So it's a Sri Lankan audience here might know it. There are hundreds of people died within the year, plus, of course, the elephants due to that. So these elephants are kind of intelligent animal. So the only solution, practical solution for that is building the electric fence. But the elephants are quite intelligent to break those fence. They know how to break it, and also they can sense whether this fence has electricity or not. If that's due to the electricity break or due to some other problems, if electricity not in the fence, they will break it and then attack the village. So that's kind of an ongoing problem. So in order to solve these problems, we kind of develop two kind of solutions which go each other. So one is a smart electric fence where we can see the breakage. So you might say that, hi Kasun, there are a lot of applications, a lot of such commercial products there. So what you do? Basically, our idea is not to use expensive things, but to use a kind of cheap device anyone can build and attach to the fence, and the communication is via the wire. So same electric wires. So that's the idea. We are not using any Wi-Fi or we are not using any 3G, but we develop cheap device which hook into the fence, and those device talks through the same wire. So same electric wire, because in those fence actually they are not continuously putting the high voltage, they do it pulse. So because if an animal touch it, so they get the shock. Soon as the power is go, then the animal actually throw away. Like they are using the pulse. So our idea is in between those pulse, why not we do the communication? So then this same wire can use to find it out the breakage. So then we don't need the thousands of devices which connect to the internet directly. Instead of, we can have one single device connected to the internet at the end, and the rest communicate through the same electric wire. So then people can see the locations of this break. And the other interesting IoT communication which we develop using infrasonic. So perhaps you know about all elephants talk to each other using low frequency calls. It's between 15 hertz to 20 hertz, which human cannot hear, but elephant can hear. They call it as elephant calls. It's a well-known, and zoology researchers has proved that this is the infrasonic calls in this range and so on. However, the recording of infrasonic calls, we need a very expensive mics. So it's $1,000 or hundreds. It's not actually 100 range, it's a $10,000 range dollars in each mic. Instead of that expensive mics, we have developed a kind of cheap mic connected to the internet. And what we did is, using those infrasonic calls, we localized the location of them. So for example, if the elephant talks infrasonic, if there are two mics in some distance, so we can measure the angle of the wave. And by measuring the angle, we can approximately tell where this elephant is, right? So of course, if they talk, if they silently attack, we cannot detect it, right? But if you start talking, or if you issue some kind of infrasonic sounds, so we could find it the location. We did some field studies in different areas, Udavalava, Anuradhapura, and then some with the captive elephants. So we have quite promising results, and we have published few papers as well. We believe surely we can localize them. Using infrasonic, we can localize the location of the elephant is quite accurate. And by improving this idea, what we plan to do in the next few years is basically deploy those devices, mics, which connected to the internet in rural village. So each them continuously record these elephant calls and their angles locally. So the mics we plan to connect to the Raspberry Pi, and the Pi is connected to the internet. And then in our central server, we get those angles, and then we publish whatever the locations of them. So anyone can see the approximate locations of these elephants, roach elephants, which approaching into the villages. So that's another kind of application which we try it with. So this communication, we always use our platforms which we develop, so which I just described already. So these infrasonic calls and the electric fence. Of course, we have kind of a home application which also communicate through this platform, which puts your homes into different modes. So for example, you can think your home as a person smart home, and it might have different moods. So like visitor moods, night moods, and then maybe a away mood where you switch on, switch off few lights and so on. So using some application, actually, you can put your home to the mood. That means you can turn on, turn off set of lights based on your interest or the status. So we have such applications already deployed in few homes, even in Sri Lanka. And there is another quite controversial social network application which we have developed based on this platform, and it's up in Google Play. You can try it out. It's a beta version out there if you're interested. So there we have kind of sacred application which sacredly share your locations, selfies, and then sounds and so on. No one can hear it in between. It's a kind of Snapchat, so you get it and disappear, but still the Snapchat can see that. But with this, even the middle service provider, we cannot see it because end-to-end encryption. So the thing is, we provide kind of a remote access. So for example, if you want to see the location of your child phone can share it to a parent phone, and then parent phone can see where the child. Plus, if you can share the child camera to the parent phone, then even parent phone can remotely take a photo from the camera and see whether he's lying. So it's a social kind of application. You can communicate with your partners and whatever the interesting parties and so on. So it's a quite controversial thing is whether you like to give your camera, remote access to your camera or the mic to someone else. So it's up to you. Maybe if you like, there are ways to do it. So you can try this app called Rahasak. Rahasak means the secret in our local language. So it's in the public domain. Right. And all these applications, as I said, we developed through our own kind of platforms. It's on the GitHub, so you could use it and customize it, whatever it's open kind of platform. And some of the source code of the applications which we have developed also on the platforms, you can get it and use it. And we developed those through a couple of Google support, this Google Summer of Codes and Google whatever the supports, we got it throughout the years. And the Elephant project which we do, I forgot to mention, the Uppsala University Sweden is funding us to do it and deploy it in Sri Lanka. I think that's it. So if you want to have some questions, I think we can use the rest of the time.
Look, I thought it'd be useful just to do a brief review of what we've gone through here. I started talking about the various applications of IoT, which are different from any applications that we've really thought about before, and then about the specific technologies that have been developed to solve these problems, such as small microprocessors, specific radio protocols, batteries that last a long time, and so on. You start with these sensors and these small microprocessors. You send your messages out over one of these specialized radio protocols, and then you send them into the cloud. But when we're talking about the cloud, we're talking about platforms like Casem's MySensors or Azure IoT Hub or Amazon's IoT offering or PubNub. In the network that I'm operating now, a LoRaWAN network, the LoRaWAN controller has API plugins for all of these different IoT platforms. And end users of the network register with the network and say, I would like my data from these sensors to be available via these platforms. And connectors are plugged in just with drag and drop and a couple of clicks. And data from one sensor is made available in a private and secure and encrypted way all the way through to end-user applications. A lot of what Kason talked about with social networking and so on is very valid because there are huge privacy concerns when it comes to all of the data that's passing around. You know, you may not think that an electricity meter should be private, but an electricity meter will tell you when somebody's at home. A water meter will tell you when somebody's at home. A tank meter will tell you when someone has taken a shower. These are all things that may seem innocuous, but they can be used to build a profile of you, of your family, and you want to keep them encrypted and private from everyone else, including your service provider. Only the people that need to have that data should have it. Right. We have a question. I think that's a good summary of what we've got, sort of the whole stack from the little bits of data into the end user applications. Please go ahead.
Jeff Houston. I was actually looking for something and I didn't see it in all of this presentation. One of the problems we face at the moment is this savage DDoS attack vector. And we understand that a huge amount of that comes from old Belkin and Linksys CPE systems out there that are rotting in cupboards. You know, it's 20-year-old software, 10-year-old software, never been upgraded, never will, dramatically lousy stuff, and it just doesn't get fixed. There are around a few million of them. The concern, of course, is that we have a few billion of them, because if we have the same problem by an order of magnitude greater, there is no internet left. It just, you know, basically dies a horrible death. So part of the issue that I think we're all looking for is not how do they communicate securely, how are they maintained in the field? Currently, the experience we have with Androids and macOS and so on is every few months these devices have to download a gig or two. This is bullshit. You know, they are handling the upgrade problem as pathetically as possible, and it disincents folk from keeping up to date. So a whole bunch of folk are running really old software because it's too difficult to upgrade, and that's on stuff they look at. The stuff they never look at just dies a death. What's the story about vendors of things maintaining the quality, accuracy, and currentness of the systems they deploy? How are we going to do that?
When it comes to the $3.50 and $7 Wi-Fi and processor chipsets, you will probably never see a software update. You're going to buy a connected toaster, it's going to connect to your Wi-Fi, it probably isn't going to have much in the way of security, and it is going to be a part of the global botnet of doom that actually finishes the internet, and then we have to turn it all off and turn it all back on again.
You see, I'm unique on this planet. I'm the only person who writes fantastically correct software that will be correct from now until it, you know, doomsday. This is wrong. I mean, all of us don't do a good job.
Just quickly, I'll say that this is a problem confined to Wi-Fi, and when you're talking about the rest of the connected devices that are attached via publish-subscribe models through protocols like SigFox and LoRaWAN and nb-IoT, there is no internet access to these devices. There is only access to a particular server, and there's not the ability to DDoS the world, because people who want that data have to subscribe to the data, and they have to have the cryptographic credentials to subscribe to that data. So the end devices, the billions of end devices with IoT protocols, will never have the opportunity to DDoS the world. The Wi-Fi ones, on the other hand, that could be trouble. Kason.
Okay, so in case of like you are mentioning about how to manage it, how the software is buggy and so on. So perhaps you may heard about there is the big vendors like Microsoft. There is a move like, so we have to move the security into the software development life cycle. So what we call software security. So instead of right now, what we do is we develop the device, deploy it, test it, and then if it is not secure, we put patch it, like a firewalls and so on, to protect those devices. So if you can incorporate the security, whatever the technology is, into the software development life cycle, in the future we might have the secure software. I don't know.
Are you optimistic that that's possible?
So we have to wait and see, I guess.
I cite my iPhone and iOS, where the business model from Apple is that I can't crack it. because otherwise you can put any old apps on the App Store and Apple doesn't get a cut, right?
Right.
Every single version of iOS has been cracked within a week. And this is a company that depends billions of dollars on not cracking it. Why do you think $3 things will be better?
So, good question. So basically in the complexity wise, so maybe it's a $3 stack. So we may not have millions of codes there. So we can thoroughly test the security and things before release it. So when you get like iOS software, there are different stacks we already developed. So time to time people might find the bugs. So that's kind of an open problem we face as a software engineers in general. So we release the buggy software. So there is an industry called security. So if you don't release the buggy software, there are no security needed. We need. Well, that's so my personal.
I suppose my concern, and I had to say it after, it's a wonderful world, and there are tremendous applications that will effectively transform a huge amount of our world. The downside is that our experience so far is pretty shocking, and multiplying the number of devices by the factor of billions that we all foresee has its downsides that we are only dimly aware of. And in some ways, we actually need a better attitude of responsibility and quality of the equipment we're deploying out there. Because so far this industry has been little short of criminal in its neglect of quality, and the DDoS attacks are basically an inevitable byproduct of that neglect.
Yes, exactly. So for example, if I take like car or automobile industry, we don't see the car manufacturer asks us to upgrade our engine. But in the software industry, so in the software manufacturer asks to upgrade the core because they release the buggy. So that's software industry. They make money out of it. So that's my personal idea. So we have to live with it.
Okay, thank you all for attending the session. I'll let you eight minutes early for your morning tea. But if you do have any technical questions, operational questions, oh, hey, there we go. Yeah. Please.
I'm Asela from Sri Lanka Telecom. Now, when you install lots of sensors in remote areas, what is the infrastructure you use to connect them to the internet?
Very good question. So most of the 20 base stations that I'm operating are using 3G, 4G to backhaul from the base station. I have what's called a private APN agreement with one of my cellular carriers, and I have direct handoffs to their network. So the data doesn't transit the internet. It goes from the LoRaWAN receiver into a cellular modem across my own private network on the cellular and into the cloud.
Say in a local, say in a village, you have a concentrator connected to 3G, and then you are using wireless low power WAN to connect to that concentrator. Is that it?
So the devices themselves use the wireless low power protocol to connect to the base station. And when I say base station, it's really, I could hold it in my hands. It's quite a small device with the LoRaWAN receiver.
Still, you'll have to have a lot of those base stations, spread around the country now, going mass scale.
It depends entirely upon the type of terrain. For example, in one part of New Zealand, we have a base station installed to cover olive groves where people are growing olives. They need to have some telemetry from within the groves. We have 20-kilometer non-line of sight communication with this base station, but it's because the base station is up high and the amount of vegetation they have to go through is quite low, only a few tens of meters. In a dense jungle environment, if you're at ground level on a level plane, you may only get 1 or 2 kilometers worth of coverage out of a base station.
Is there any possibility for you to collaborate with the mobile operators for having, spreading the base stations?
Absolutely. Korea Telecom has deployed a LoRaWAN or is deploying a LoRaWAN network across the whole country. One of the Japanese operators is deploying both nb-IoT and LoRaWAN across the entire country. A number of mobile operators around have deployed these LPWAN technologies because they know there are requirements beyond what they can satisfy with 2G, 3G, GPRS communications.
Okay, thank you. That's fine.
You're welcome. I'm sorry, any more questions? Samit, please.
This is Samit from Walling Communication, Nepal. Thank you for giving us great insight of IoT and the usable applications. My question is there any development going on to integrate the IoT technology on the seismograph to have earthquake warning detection systems?
Yes, it's absolutely possible to set a seismograph to a LoRaWAN transmitter to take the data out. Now, in New Zealand, there are seismographs at more than 100 locations because we have a lot of earthquakes. We have a very unstable geography. Right now, most of those receivers are backhauled through satellite, but some of them have been converted to using Wi-Fi. Now, Wi-Fi is okay, but it's not as good as these new protocols. So I wouldn't be surprised if our organization, the geotechnical organization, shifts some of their seismographs to the LPWAN technologies. You're welcome. You have one more? Okay, please, to the microphone. Can you help him to the microphone? There we go. It's coming.
Okay,
Thank you
very much. I was very much hopeful to know that the Internet the things. Like, I'm the blind person. I came here in this conference. I have my smartphone, a smart cane, everything, but I cannot move around. So if there is any Internet in my cane, then this Internet could guide me to go around without anybody's help. That could be a big, big achievement for people who don't have the vision. So what do you think? It is possible? Thank you.
I think that today most of the advances are in machine vision, taking advantage of smartphones with their cameras to map the environment in real time and interpret it. But the ability to have things like Bluetooth Low Energy to locate devices can be very helpful. I'll just try and find my keys using the Tile app. I don't know if the Tile app has been improved to help. Yeah. So what happened? Some of you heard it. It was very faint, but I used the app on my phone, and I said, locate my device, and my keys started to sing. I think this is useful. I'm sure your hearing is pretty good, and if you were in a room without, a few hundred people, you might be able to find them very quickly. You're welcome. Okay, and now